This is the part where we connect what you just heard earlier today about cloud computing and scalability with software as a service. So in terms of our picture, we are now here. Okay, we've done the top tier, we've seen HTML and CSS, and now we're going to take a closer look at what happens when something hits a website. What does that mean? What is a website actually composed of? So in the olden days, most websites were just collections of plain old files, not very exciting, but as soon as e-commerce became a thing, what you realize is actually to generate the page, you're going to run a program, and the output of the program is going to influence what you see on that page. And originally people did this by saying, okay, no problem, we'll just make HTML files like always, but in a few places inside that file, we're going to have a place where you could run a small piece of code and substitute what the code does into the file. So it was still kind of about HTML, but you could selectively put the output of pieces of code in there. And after a while, the code got so complicated that this became the tail that wagged the dog, and people said, okay, we need a better way to do this. Instead of starting from the HTML and figuring out how to stick code in there with a shoehorn, is there a more graceful way to build these kinds of sites? So if you're going to run a program to generate a page, that means you need to solve a handful of problems. You've got to figure out, given a URI that's coming in, what program and what function within that program should you be calling? What if you need to pass arguments to it? How would you do that? What if you need to store things across requests? For example, if the user's in the middle of buying stuff, you need to remember what they're buying so that when they go from checkout to payment, their shopping cart won't be empty. So there's a number of common tasks that sort of come up over and over again, and that should trigger design patterns, right? There's going to be a way to solve this. One of the patterns that arose to handle this is, well, we can actually divide these responsibilities up into three kind of big categories. And they've come to be called the three tiers of the three-tier architecture. The presentation tier is the thing that actually interacts most closely with the user, right? Presents content back to the user. That's going to be a web server like Apache. The logic or application tier is where your app actually runs. That's where kind of interesting stuff happens, right? The thing that makes one site different from another is what's going on in the app tier. And the persistence tier, which is handled by a file system or a database, typically is information that's got to survive over the long term or across from one request to another. So over time, as this architecture became sort of the way things were done, frameworks began to evolve to support these common tasks in terms of the architecture. And as we'll see, Rails is exactly one of those. Now, this same architecture, surprisingly, applies whether you're developing on your own machine or whether you're deploying to the cloud, right? If you're on your own machine, you might be interacting with a local web server, and we're going to use WEBrick in our exercises and stuff. The application tier in purple is going to be the Rails library and an application server called Rack, and a really, really simple database called SQLite that's just enough for you to do development on your local machine. But that same app, if you're going to deploy it in a real environment where you have to serve a lot of users, well, boy, now you actually need a bunch of copies of the logic tier, right? That's the purple. And maybe, if you're clever, in front of those, you're going to put some machinery that will remember or cache the most frequently accessed pages so that you don't even have to run your app to generate those. And there's a whole bunch of keywords that, software that people use to do this now. This is kind of how you used to do, if you took this class a year ago, you would have had to do this. In fact, there's now even a better way because of cloud computing, is we're going to deploy on Heroku, which is actually built on top of Amazon EC2 that you just heard about earlier. And Heroku actually hosts thousands and thousands of apps in all different languages. They provide their own databases, which they manage. They do caching for their database, which they manage. They have a grid of workers that they call dynos. And the idea is they've got their own machinery for figuring out when someone's using your app, locating the right dynos that are running your app. And if you need more capacity, they just add more dynos. If you need less, they scale it down. It's a beautiful thing. Okay, so what's common across all these pictures? Light blue, presentation. Purple, logic or application tier. And dark blue is a persistence tier. This architecture is pervasive. Now, why is this important relative to cloud computing?
When Dave talked about cloud computing, he pointed out one of the advantages was that, in principle, you can add and release machines on demand as you need them. And we could imagine that we already talked about HTTP and how it's a stateless protocol. Every request is independent of every other request, even if those are coming from the same browser and the same user. So you can see how that's a useful property, because in each of these three tiers, in the web server tier, well, we can just add more web servers if there's more demand. We could also add more machines in the app server tier. And you might ask, well, why would you actually need two separate tiers to do that? As it turns out, the amount of work that a web server does per request usually is a lot less than the amount that the app server does per request, right? Because remember, the web server is really just dealing with the connections to the different clients, but the app server is running all of the actual code of whatever your app does. So it's not uncommon that, for every web server computer, there'll be several app servers to sort of soak up the load. Where it gets a little bit trickier is in the persistence tier. And for reasons that are described somewhat in the book and that we'll come back to when we talk about some more advanced topics, you can't just replicate your way out of scaling the database out. You can't just create many copies of the database, even though from a capacity point of view, you really wish you could do that. So what do people do instead, given that the database sort of quickly becomes the bottleneck? This slide summarizes what is now, I think, one of the most active areas of research in distributed systems and cloud computing, which is how do you scale storage to handle really large amounts of data? Not just for web apps, but also for bioinformatics, for genomics, for things like traffic and maps. So there's a couple of different strategies, and typically any given site is going to use some combination of these. One of them is called sharding. The idea is that you actually break up the data into separate chunks. So for example, you can imagine for keeping user profiles, you could split it up by the user's last name or by their username. Any app server has to be able to talk to any one of these because when a user with a certain username comes in, you don't know which app server they're going to be assigned to. And the good news is that this scales really well, right? The more load you have, you can make the partitions smaller and smaller and just have more and more of them. But it turns out that if the operation is something other than look up a user, then it gets really bad because now an operation has to touch more than one storage container. On the other hand, you could say, okay, well, we'll just make multiple copies of all the data or copies of large chunks of the data. And that means that when we have to touch multiple different tables, those queries will be fast. Unfortunately, it turns out that doing a write to a database typically takes much longer than doing a read. So when you do a write, whichever one of these three you write to, eventually what you wrote has to propagate to the other two, and that takes a finite amount of time. You could do a lot of engineering and bring that time down to sort of hundreds of milliseconds, or in some cases even less. But for example, Facebook for a long time had this issue that if you did a wall post, somebody on the opposite coast might not notice it right away because the data takes a certain amount of time to propagate from one of their servers to the other. And for a while, I don't know if they still do this, but they actually were addressing this problem by whenever you did a write, you would be temporarily pinned to the one and only copy of their data center that accepted writes. And for a couple of minutes, everything you did, even your reads, would go to that copy because then everybody could, you could immediately see what you just updated. After a while, you'd be flipped back, and the idea is that it was enough time for whatever you did on the primary write server to have eventually propagated over to the secondary server. So again, we're not going to try to solve this problem in this class, although great project, right? But this is a really, really active area of R&D in cloud computing, and there's a great quote that I think we used in the book from an engineer at Heroku, who, their whole business proposition is, we will scale your app for you. And he says, I often get the question, how do you guys scale the Postgres database? And he said, the simple answer is, we don't. I could tell you about how we do sharding, and we have database caches, and we do all these clever engineering tricks, but at the end of the day, relational databases have a limit on how far they can scale. And at some point, if your app becomes big enough, you end up having to confront that directly. It's not likely your projects will become quite that successful by the end of the semester, although that would be cool. Okay, so to summarize, what we've seen for kind of Web 1.0 and how it evolved software as a service, we've seen that a browser requests things using URIs. Those are transmitted over HTTP. In the SaaS world, a URI is really a way to run a program more than a way to fetch a thing. HTML and CSS are used to encode what you see. Cookies allow the server to track a client because the client is responsible for making sure that any cookie that it gets from the server is provided whenever that server is visited again. And usually what the cookie does is it includes enough information to let the server dig up a little packet about you that it has stored since the last time you were there, which is why some sites just don't work if you turn cookies completely off. There's no way for it to track that it's the same person coming back to subsequent page visits. And all of these abstractions are so common across all SaaS apps that frameworks like Rails and others have evolved to sort of make it easy to use these without dealing with a lot of the details directly.